Good morning, everybody. Let's start the session. This is AQC 2016. This is the fifth of the series, and we have, I heard, 180 participants this time. It's the biggest one. So the field is expanding exponentially. So the first speaker will be Hartmut Neven from Google.
Good morning, everyone. So on behalf of the Google team, I would like to welcome you all. We're very happy and glad you could make it. And hopefully we have a few interesting and fun days together. As Nishimori-san said, we were pretty astonished and pleased to see that there's quite a growth and maturity coming to our field, in the sense that we had about 100 submissions this year. And even though we went for the first time for this conference double track, we still had to reject about half of the submitted talks. And as always, there's a random element to it. So for those where we unfortunately had to relegate it to the poster session, please don't be sad about it. And inversely, please check out the poster session, because there's a lot of high-quality talks in there as well. So getting to the scientific part, I wanted to kick off this conference with some optimistic notes. I happen to be the optimist on our team, and I wanted to share with you an argument why I think quantum annealing is going to succeed, and why I believe in the next 1-2 years we are going to gather conclusive evidence that this is indeed the case. And I have a little argument I want to walk you through rather quickly. So the first point of observation is, this was our December paper, and all details will be presented in the next talk by Vasil Denchev. But essentially we saw that for a crafted proof of concept problem that had a very rugged energy landscape characterized by tall and narrow energy barriers, quantum annealing did better, much better, than its classical counterpart, thermal annealing. And then, moreover, since then, we looked closer and found, not surprisingly, this is not a rare phenomenon. Actually, you can use a tool. I would like to refer you to the talks by Helmut Katzgraber, Zheng Zhu, and team. So Helmut developed a measure we refer to as P of Q. I will not explain what it is, other than to say you can use it as a litmus test to characterize the landscape of an optimization problem you're dealing with. And then if you find that in this landscape, or in the ideal case, again, you have tall and narrow barriers, but not any broad barriers, then you find in numerical simulation that simulated quantum annealing, in our case is simulated by quantum Monte Carlo, succeeds much quicker than the classical counterpart again. But actually, the inverse is also true. You can use this litmus test to find many examples where quantum annealing is not doing as well as thermal annealing, which leads to the conclusion that what you really want to do is you don't want to have quantum annealing fight on its own a portfolio of best classical solvers. What you need to do, you need to combine the best of both, of thermal transitions as well as tunneling transitions. And we have recently developed an algorithm we call the quantum parallel tempering algorithm, which achieves this. And so let me quickly explain to you how this works. I'm sure most of you are familiar with traditional classical parallel tempering, very similar to simulated annealing. The difference is that you don't have one temperature parameter that you dial down from high to low, but rather you produce replicas of your system, and they live at different temperatures. Each one follows a metropolis dynamics, and then you have metropolis swaps between those replicas, and this elicits this diffusion process where eventually you have the best solutions winding up at the cold temperatures. But by what I said earlier, you should expect that if you have a large optimization problem, you will have all kinds of barriers. You will have the tall and narrow kind, broad barriers. So what you should expect that if you just run it classically, then there will be groups of spins locked up behind tall and hopefully narrow barriers. And in that case, you would benefit from just extending the scheme and running annealing a little bit different than we normally do it. You would have, again, this classical column, but then every once in a while or after every outer loop, the quantum annealer comes in, grabs the replica, initializes the annealing process at a classical state, then you dial up the transversal field to a certain gamma max, you don't know exactly necessarily what this is, and dial it back down, take that replica, and again, if there was a group of spins locked up behind a tall barrier, there's some probability you will find those spins on the other side, and you would readmit this state back into the pool of replicas, again, by metropolis rule. So we think that in this combination, you get the best of both worlds, and we think or expect that, or the question you should ask now, how would we know that such a scheme has a chance of beating the best non-quantum enhanced optimization algorithms? And there's a long list of reasons, actually, why we think that's to be the case. For example, again, look at talks by Hartmut. You will find that the classical parallel tempering scheme alone is highly competitive with the winners of the set competition. For example, there's a paper out in the archives that shows that it beats CCLS 2015, which was last year's winner of the set competition. We also know that if the connectivity graph is sufficiently dense, then methods based on cluster finding or methods like the HFS algorithm that exploit the existence of subgraphs that are nearly tree-structured, those algorithms are going to fail, going to cease to be effective. And I would check out those talks. So therefore, I feel we can, I would like to make the following prediction, that if you integrate quantum annealers that feature sufficiently dense connectivity graphs, that's important, into a parallel tempering scheme, then you can attain speedups that are practically relevant. And actually, from a Google perspective, that's how we envision eventually an optimization service to work like. I mean, this is what we would like to offer our customers eventually, that folks, internal or external, who have optimization problems, they send instances to a service, and there the service will return good solutions to their optimization problem. And the nice thing about this scheme is you can build an asynchronous service architecture, where you essentially have a big server in the middle that hosts the replicas at different temperatures, and you have running the baseline algorithm, local stochastic search, realized by metropolis updates. So you have these replicas living there, different temperatures, going through their metropolis dynamics. That's the heart of the algorithm. But then you have, at Google, we would call it a worker pool. You have specialists who come in and say, oh, I have time right now. Give me one of your replicas. Let me see whether I can help you with an update. And there, again, if those problems live on sufficiently dense graphs, we will find that a quantum annealer eliciting tunneling transitions as described before will be able, or we expect it to be able to give you good updates that you would readmit back to the replica pool. And that this particular move will not, using any classical technique, would take much longer time. But in this scheme, see, in the past we have always done this bake-off, quantum annealing against everything. Here it's more like a judo move. We say, we understand much better now what quantum annealing is good at, and do the quantum resources do what they're best at. Again, that is dealing with rugged energy landscapes where you, on a dense graph, where you try to explore the energy landscape and find a lower minimum. But you can mix and match this with any type of classical update you like. If your problem admits for cluster updates, use those. If you see there are subgraphs which you can update quickly by classical methods, do this. So essentially in this scheme, anything you can do classically to advantage, you can use it. And the nice thing is also because the core of it's a replica server as a classical object, you can instrument it and take measurements there. You can, for example, look at replica overlaps, and to be explained by Hartmut. You can look at time correlation functions, and this information can help you to guide the flow of replicas through the system. And you can even get rather fancy putting machine learning on top to see that sort of the flow of replicas is optimal or sufficient. That kind of service, we hope to do sort of diligent benchmarking work and show that in such an architecture, having quantum annealing there will be a valuable member of this architecture, helping with certain types of updates that in the, let's say, 500 nanoseconds or 1 microsecond that an annealing run would take, that you wouldn't find any classical schemes that could do a competitive move in that short time. Okay, so that is the reason why I'm rather optimistic. And now you may say, okay, fine, I've introduced this architecture, but when you are faced with a true NP-hard problem, you haven't changed the complexity. This still looks like exponential time complexity. Or inversely, you might just be able to lower the residual energy by a few percent. So the complexity theorists may say, not much achieved. But from a more economic perspective, I would say a lot is achieved. Because even a few percent improvement along important product dimensions is very important. And why is this? Because the internet has brought us markets with near perfect transparency. So this leads to this winner-takes-most phenomenon that if you have a product that's just slightly better than the next product, people will buy your product, not the next one over. And therefore, we should realize that every computation happens in a context. And that context may, what starts out as an initial small gain, could exponentially amplify it. So we should not dismiss the ability to think of it more as interest rates, rather than sort of what has been gained in absolute. Think of you have increased the interest rate a little bit, and then think of what's that going to do over a few years. And that may be a somewhat odd remark, but this very phenomenon makes me think that I find the field of quantum biology quite interesting. And I think we will see more quantum biological effects for that very reason. If there's a bunch of cats out there, and we talked about the dangerous road, if one of them has a little bit better, or some of them have a little bit better car detector, that's the only type of cat you will see around a few generations later. So I think it's important to keep that phenomenon in mind. So yeah, this concludes my upbeat assessment of why I think that quantum annealing will be very worthwhile to invest into. I want to finish with one last shameless plug, and that is we have taken the liberty to interpret the theme of this conference a little bit broader, in the sense that quantum annealing is really the prototypical and in some ways the first pre-error corrected quantum algorithm. But there's more now, and in particular we are quite excited by the possibility what you can do with shallow quantum circuits and what pre-error corrected quantum algorithms you can do there. And I would like to point you to a talk that I think will be very interesting by Sergio Boixo and co-workers, showing how to reach quantum supremacy with near-term buildable shallow circuits. Yeah, so if you forgive me this plug. I will conclude with wishing you all to have fun here the next days at AQC 2016.
Thank you very much. I should ask you to come here for a question to record. So do you have any questions or comments? No questions? Well, that's strange. Please.
Yeah. Well, I didn't understand. Hartmut, I'd like to ask you something. Hartmut, I'd like to ask a question. That's part of the session, right? What I didn't understand in the tempering thing was when you go to the middle server and you find a configuration, that's something diagonal in the Z basis, right? And then when you send that over to the quantum annealer, you're sending something which is diagonal in the computational basis, right?
To start out with.
Yeah, so then what happens? So then what's...
So now you dial up the transversal field, and this will start sort of to spread.
Oh, so
the
when you
wavefront.
send it in, the transverse field is 0, and
Yeah,
then
exactly.
you turn it up.
Exactly.
Okay, got it.
And to a certain strength, and we don't know which strength this is, so we will try a few gamma max, and then...
I just missed that. Okay, thank you.
That's a very interesting aspect. Any other questions? Yeah, please go.
I'm not very, hello, I'm not really an expert on the domain, but I would like to know what is the definition of replica. Is this replica a notion related to statistical physics system? Can you in for dummies explain what replica is? Really.
Oh, so sorry. I was under the impression that everybody is quite familiar with parallel tempering. So replica simply means that you have the problem on the same graph. So you're in D-wave language, the HIs and the JIJs would be identical, but the replicas can differ by the exact spin configuration because each one goes through probabilistic metropolis updates at different temperatures, so the evolution will be different. But each replica lives on the same identical graph with the same values characterizing the connectivity and the local fields.
Thank you.
Once again, to go on to the